So there's one force that we haven't talked about, and that's the applied force. This is just a catch-all for any forces that don't fit underneath all of the other things. So like if you had an actual person pushing on something, that would just be called the applied force. Okay, so today we're going to talk about free body diagrams. And they're also called force diagrams. Basically, these diagrams are ways to describe all of the forces that are acting on a single object. So the first thing that we need to do is define like what our object is. In these pictures, the object is just the rock. But if you think of that you could have like a train, right? And you have all of the different cars on the train and they're linked together, and then you have the engine of the train, smokestack, that you could think of this train as an individual car, and so you could think of all of the forces on one car of that train, or you could think of it as the whole train and what forces are acting on the whole train. And so that's sort of defining the system. Okay, so for this, our system is just going to be, excuse me, the rock. All right, and so when we draw a free body diagram, we start with a dot. That dot is at the center of mass. It doesn't really matter that you don't particularly know what that is. We'll describe it later if we need it, but the dot goes sort of at the center of the object. And then all of the forces are drawn as arrows that the tail starts at the dot and the arrow tip moves away from the dot. And those arrows are drawn with the length corresponding to the size of the force. Small force, small length of the arrow. And finally, we'll label our forces using on-by notation. And so even though they've given a dot for all of these forces, I'm going to draw my free body diagram or my force diagram to the side. And so let's just start with the easiest diagram of a rock sitting on the ground. What forces are acting on that rock? Well, we have the force of gravity that goes straight down. So instead of labeling it F sub g, we're going to label that the force on the rock by the earth. And then we have the normal force or the support going up. This is the force on the rock by the ground. A lot of times when you see forces written, there might be a little arrow above the F. That just lets you know that the force is a vector, meaning it has direction, rather than a scalar without direction. So quantities that have direction, oftentimes you'll see with this little arrow above. Now, please feel free to abbreviate R and E and G. So on this rock, then, I'll let you do the second one by yourself, and I'm going to move on to this guy here. So we have friction that's going to prevent this from sliding. So the forces that are acting on the rock, I'm just going to draw them where they appear, not correct free body diagram, but we have the force of friction that's going to go up, and I'm just going to label it as their names. We have the force of gravity. The force of gravity always acts at the center of mass. And then we have the normal force. And so if I were to draw this correct free body diagram, then we have the force of gravity that goes straight down. This is the force on the rock by the earth. We have the force of friction that goes up. This is the force on the rock. And I'm going to just go by friction, but that's going to be the surface. And then we have the normal force. Remember, and that's perpendicular to the surface. And so your normal force and your force of friction will always be perpendicular to each other. So this is the force on the rock by the ground. Okay, so these rocks have tension forces, and we'll talk more about later how you know how big to draw tension forces or which forces would be big or not. So really at this point I'm just mostly concerned with you drawing the forces in the correct directions. And so the tension force here, we'll maybe call this 1 and we'll call this 2. And so here I have the force on the rock by string 1. And then I have a force pulling this way. This is going to be the force on the rock by string 2. And then again, the force of gravity going straight down. And so this would be the force on the rock by the earth. Now I know you're wondering to yourself, what is it that this says that this is in equilibrium? Like all of these have been in equilibrium, where now this one says that the rock is sliding. Equilibrium just means that the forces are balanced. So all of the x component forces, all of the left component forces equal all of the right component forces, and all of the up forces equal all of the down forces. We'll talk more about this later, but equilibrium just means that your rock is not accelerating. That does not necessarily mean it's not moving. So it's either stationary, so you can have stationary equilibrium or static equilibrium, meaning not moving. Or you could have dynamic equilibrium, meaning moving at a constant velocity. At this point, it's not really important that you know how this rock is moving. So you guys can go ahead and do number 9 here, that the rock is sliding on a frictionless incline, so that there's no force of friction on this free body diagram. So you guys should be able to do the rock falling. There's no friction again here, meaning there's no air resistance, so there should only be one force acting on your rock. I'm going to come and do this one though. This one is falling at a constant terminal velocity. Terminal meaning the end velocity, so it speeds up, it goes faster, 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 and then it moves at a constant rate. And in order for it to fall at a constant velocity, it has to be in equilibrium, meaning the downward forces, the force on the rock by the earth, have to be equal to upward forces, the force on the rock by air resistance. So whenever I put little hash marks like this, that means the forces are equal. All right, I'm going to put the question numbers that you're to do for homework on campus. So some of them I'm going to have you skip over because I'm not mostly concerned with those at the moment. So good luck with your free body diagrams, and I'll be available if you have any questions.